Okay, so this video is on quantization in large language models. We're going to cover the basics from like just what we mean by quantization and then how we've adapted that in large language models. The first part is basically what is quantization, and it's pretty simple stuff. But the first thing is what can we do with it directly before we start to consider actual LLM sort of custom stuff. Okay. So yeah, so basically we're just taking a number and we're trying to make it smaller. In FP16, it takes 16 bits, 2 bytes, which for a 70 billion model is 140 gigabytes. If we can get it down to a byte per weight, say by int 8, it's half the size, int 4, it's a quarter of the size. Great, you know, smaller, better, faster, it's all good. And by the way, we'll consider floating point ones perhaps later or another video, but this is just going to talk about the basic sort of theory, and so ints versus integer weights. So the first thing we have to acknowledge when we talk about quantization is what we are quantizing, weights. You know, obviously the real ones are many, many, many billions, but here we're just going to consider a small block of weights. So here are 64. Right, and if we look at the numbers, what we find is they tend to be a bit like this small example. Most of them are near zero or around about zero, sort of all these sort of bluey ones, these sort of dark bluey ones, grey, and then there are a few outliers which are way off zero, maybe 1.78 minus 1.4, you know, or around about -1. The actual outliers can be quite vastly more than the outliers in this, but there's still relatively low number of them compared to the most of the weights around zero. So normal sort of statistics, you know, the classics of the scientific method, we quickly throw away all our outliers, but that doesn't work for weights because there's a lot of energy, a lot of important stuff in which bits are outliers. So the idea of just kind of just throwing them away and not worrying about them doesn't work at all. So when we're talking about quantizing, we need to think about how we're getting them from this floating point real number system into integers. And essentially, you know, it's pretty simple, but an integer of a certain bit width has a number of finite steps between 0 and, you know, -4 if it's a 4-bit or whatever. You know, it's just basically two constant math. So you've just got all the integers between some positive and negative number depending on the bit width. So if we're 4 bits, sorry, we've got 16 values, and we just snap down, right? You know, if you've got the number 1.5, it's going to end up being either 1 or 0, depending on which way you round. And obviously, the lower the bits, you have fewer ticks on your number line. So, you know, you can pretty easily see why low bits get harder, and just having more higher bits, number of bits helps because there's just more ticks to snap to. So the easiest way to quantize is simply just to literally cast it, just round it down, right? And this proves to be pretty catastrophic always because of those two properties, right? Without any kind of adaptation, if you're, you know, int 8, your numbers go from -127 to 128. All your ones get between 0 and 1 pretty much get mapped to 0 to 1. And, you know, and probably you don't use most of the range because, you know, in our original 64, if we just show it back here, you know, the maximum value we got was 1.78 and 1.5, 1.4. So, you know, you're going to waste most of your numbers. In fact, if you look at this, we actually end up with only 4 different values out of all our 64 errors. You know, because that's how it maps. Everything maps to -1, 0, 1, or 2, which is pretty crap for our 64 floating point values. So the next kind of obvious way is to actually scale and bias so that we're using the whole range of the integer, right? So pretty simple. We decide on what the maximum value is, we clip it, and the minimum, and then we choose a scaling value and a bias value to map as many of the weights in between those top numbers. And of course, there's an interesting thing about what values we choose to clip. Also, can we choose to whether or not we accurately record the outlier or not. So if we choose a clip that's lower than the outliers, they will get maxed at the clip range. Whereas if we, of course, make sure we can capture them properly, we have less ticks to map to. And you can kind of see again that with this scale, it's a lot better than nothing, but we're still only getting at 3-bit a few values if we want to try and capture all of them in there. But you can sort of see at 4 bits, maybe 5, 6 bits, we're getting a reasonable amount of data kept. I mean, it's still nowhere near what we'd be happy with, but it's getting a bit better, you know. And you can see that we can easily calculate the mean error, so you can sort of see how this affects the ultimate error just by that. So the actual solution that makes sense, and you can probably imagine, and what all LLMs use, is block scaling. We choose a finite number of the real numbers, and we choose a scale per that size block. The main block sizes you see are 16 or 32. Just happens to work in hardware mostly, but you can choose other block sizes. And what you find is this radically changes the picture, and it does it for 2 reasons. One is that obviously with more scaling, you're scaling a fewer number of data points, you're more accurately representing that range, so you're able to more tightly fit the data. But the other key value, which is kind of unique to how we use them at LLMs, is the outliers only affect a limited number of bits. This is integer quantization we're talking about now. So an outlier actually affects all the precision of all the near zero numbers. And because we're isolating its outlier to just the block it's in, it means blocks without outliers get really, really accurate data around things. So if you imagine this line here, its maximum minimum are tiny. I mean, like 0.21 and 0.23 minus 0.15. And the integrations, the scaling means that basically that whole range is being covered. So this thing is actually stupidly accurate because it's got, say, for 4 bits, 16 values between minus 0.15 and 0.23, which is pretty accurate. And whereas these ones that need the outliers, yes, these might be not that accurate, but we still kept the outlier, which is really important. So block scaling is used pretty much universally through LLM, all the LLMs. And you can there's a similarity here. You can kind of see that, yeah, it really can make the error rates are just ridiculously, here we were a 4-bit, and let's freeze that to actually not clip anything. And, our error rate is 0.06 for this, and you can kind of see that how badly it collapsed the values. Down here, we're already much lower. That's about me tuning it and doing the right scalings and that kind of thing. But there is a cost. This is slightly bigger, because essentially as you go down this list from no scaling to block scaling, you're actually storing a little bit more data. For the no scaling, it's just the quantized values. For the global scale and bias, there's just the float numbers for the whole block, the whole tensor. There's one scale and bias. And for the block scale, in this case 16 but n values, you're storing the scale and the offset. Now, in actual fact, in almost all cases at the moment, we only store the scale. This is known as symmetric block scaling. There is asymmetric, but in general, it doesn't kind of work well enough for anyone to bother. Okay, so that's the first, it's hopefully pretty simple. Any questions on that? Good. Okay.
Actually, one small question. I think we've talked in the past about when storing and like versioning any sort of quantization artifacts we do, the need for storing, was it auxiliary buffers? And I actually meaning to look up what they contain. Does that contain things like the scaling factors that you're talking about, or anything else?
Yeah, so there are essentially, there are two ways people do it. There is the kind of auxiliary buffer where you store the scale separately, and then there's where it's inline. The hardware always wants it inline. it has no concept of even though if internally it sometimes stores it separately. So you'll predominantly see that now separately, but it still can be useful to sometimes separate them out. Yes, but it's increasingly becoming inline now. Yeah.
And so inline would just be part of the original tensor, just as another dimension or something like that.
No, it will literally be in the data. It's a mixed data format essentially. So there would be 6 quantized values, then a scale, 16 more, and that's what the hardware actually will consume.
Okay.
It gets a little bit weirder with some of the NV forms because they have a tensor scale as well. So they have both essentially. They have one number that's kind of for everything and another one that's packed in, and yeah. Okay, so moving on to again a little bit more in the interesting stuff. So what we just described is known as round to nearest, because it's about all you can actually do if you don't take the data really into account, right? The quantization is fundamentally a lossy process. There's only so many ways to get a floating point real number into a quantized, a smaller integer number. That you fundamentally there isn't many ways of doing it. How you can win, how LLMs are able to actually use this in practice is we're able to, because we know how the data is going to be used, we can manipulate the data itself to make it more quantizable. And that's essentially these two techniques here, which have become the kind of industry standards. GPTQ and AWQ do. We understand how we're going to use the data, so we can manipulate the data before we quantize it. I think that's the best way to describe the overall thing. So when it comes down to it, we always know that our weights are going to go through the neural network, which ultimately is a bunch of big matrix multiplies. And so we can observe two things that are false, that aren't true for LLMs. That is, all weights matter equally. Conceptually, there's this huge array of weight numbers, billions and billions of values. But in practice, particularly when you start looking at what's actually used by an LLM doing a job, they're not all as important. Some of them can be completely removed, which is an entire different process called pruning. But the point is that some weights won't need their bits preserving more than others to keep the model running as well as it did. The other, which is I think a little bit more harder to sort of get first time, is the fact that the errors that you include are not an error in individual. A weight is never on its own. It's going for a matrix multiply. So even if it's got an error, you can compensate for that error in the rest of the calculation. If you can kind of steer the errors, essentially adding intentional errors later in the calculation, either in the actual matrix multiplier or in a further layer, you can kind of recover the error because you beforehand knew that weight down there was going to get it wrong. And this idea that you can tune the errors so that the later parts are able to recover, are able to improve the earlier errors, or able to fix some of the earlier errors, is the other approach. And that's called QPTQ. These acronyms get me every time. And the one about the not all weights matter is called AWQ. And the interesting thing about both these approaches, they're weight only, and they use calibration data. So we push real data through the calculation or simulate it, and we're able to characterize the actual weights, the layers, and how the neural network and the model will work, so that we can kind of work out what's important and where we want to preserve more bits, get the numbers more accurate, and other places where we can say, yeah, we don't really care about that. And that's the basic approach of how it's able to work and how model quantization is kind of currently done. So the first one is how you calculate this, right? So, and it's pretty simple. Again, you minimize the output error. So rather than trying to the obvious thing of treating a weight as an individual thing, you simply look at the output and say, was this better or worse across all the weights versus one's individual weight? And to do that, you have to actually do the matrix multiply. And the matrix multiply is going to be made of your weights and your activations. Now, normally, activations are the real thing. They're the actual, what's being put through the neural network at that time, the model. So that's where the calibration comes in. We essentially feed in semi-real activations that we've recorded from like data that we want to actually query the model on. And we determine which activation is important and therefore which weights they will be touching the most. And you can kind of see it here in this not very good diagram. This line here is our activations. Most are 0, and there's a few orangey ones that are bigger. And this is our weight field, which, because we don't know anything about it at this point, is just gray values. It's all like, this is just data. We can't determine which of these is important. If we compute the weight error at the end and push this through as calibration data, we can tell that some of these weights counted more at the end. So here, this activation was large, and you can see it affected these weights really importantly. Right? This column here is important. We know this because when this activation comes through, which is we've calibrated happens, this is great. But we can also tell the opposite a little bit. We can see that this activation value didn't really need these weights, right? It needs this one, but it didn't really thing. So we're able to bring up a map of what is important in the weights by simulating what is actually going to be used by the model, which get activated. And if that's the case, we can then, when then comes activation aware weight quantization, we empirically, and the research has shown that you can basically only 1% of all the weights are actually important enough that if you preserve them at a higher precision, you will actually get almost all of your accuracy back, which is kind of quite an amazing figure, because it's essentially, it seems to indicate that if your calibration is good, about 99% of your weights aren't actually very important. But there's a lot of research on the whole pruning and side of things of actually looking at that more, because quantization seems to show that actually a lot of the weights, they're not 0, but they're actually not as important as just a few 1%. Now, the practical way when you first hear about this of doing this is you would say, okay, so we're going to store these important weights in a high precision. Maybe we're going to store them in FP16 or something, and the other weights we will store as 4-bit or something. Now, when the paper was written, and there are very good reasons even now, that's not a good idea, because the actual hardware is going to do a big block of data, and it wants things to be roughly the same size. It's very difficult to pick out 1% of the or it's been more difficult than it's currently worth doing, 1% to be higher precision and the rest lower. So what the paper did quite cleverly is it doesn't mix the types, it scales them. So it goes back to that original diagram of the ticks, that if you can adjust it so that your important weights, the scale is biased towards your important ones, and your other weights are biased in such a way that they get quantized badly, you can get away with it. And so this is actually how it works. They calculate via this thing here, doing some diagonals and stuff, a scaling strength. And what you're doing is essentially you're picking which of these, if you think of this as the green is the error contribution, and this is how it's after it's been scaled. All you need really to find is where the errors are least across the thing versus the scale, right? So as you can see here, a high A doesn't actually affect these two important weights, and whereas that was beforehand, they're all important. And this is a search, so it's pretty simple. You can do it. And this isn't the best algorithm for this thing, but it says this is actually the best factor that you will scale your weights by to preserve these channels better than these channels. And because we know that they're the important channels, in theory, this gives you your a better error rate, a lower error rate in your weights. And that's basically is APQ. It's actually very, very simple once you kind of get the idea that you can determine, you can figure out which weights are important, and that's kind of the harder part of it. Now, one of the interesting things about this is it sort of feels like this should be a hard thing, but in practice, it's found you can literally just, you take your calibration and you argmax them, and the activations with the highest values are the ones worth preserving. There has been some work about doing better ways of doing this, but at the moment you just do this very cheap sort of argmax across all your calibration activation weights and go, right, they're the ones we're going to scale to preserve, and it kind of works. So this is the other one, GPTQ. So what we're doing here, and this is a little bit harder to kind of explain to a certain degree and understand, is we know that the weights are going to be calculated column by column. It's a matrix multiply, there's layers, so there is an order to the calculation. And we can compensate errors that occur in earlier columns by adjusting the values, the weights in the later columns, to compensate us back to where we would have been if the error wasn't there. As I said, this is a little bit unusual because it seems hard to fix a error later, but it's worth thinking. It's something like the diffusion. You can think of it like that. And if you know the classic graphics algorithms for doing error diffusion for printing in black and white, for example, how you get grayscales. This is actually Floyd Steinberg. This is the sort of similar type thing. The idea is that by moving the error kind of later, we can actually, when you see the whole thing and in an eye or in the weight, we can actually get more back to the original value, even though we've actually introduced deliberate errors almost that just cause the value to be where we want it to be. It would have been if we hadn't quantized. And so if you, and it only really works, worth noting, because the data is huge. If you don't have enough data, this won't work because you don't have enough places to correct. But if you just sort of watch this, well, how it works, you can see right at the beginning here, the RTN, the original quantized value, and the GPT value have no difference at 3 bits. But only after you've quantized enough columns, but we're able to start to introduce the error correction in, that we actually start to bring the GPT value more into line. This is a measure of the error, because we're able actually on this, these tiny little changes all the way to here, we've now got enough of one to actually pull our final error back down. Yeah. So the hard bit is, or once you've got that idea, is then, okay, how do you calculate this? And this is where it gets a bit complex. So it inherits an idea from, and I said this last time, and I said this time, one of my favorite named algorithms, the optimal brain quantization algorithm. And that uses a Hessian. So a Hessian is the second derivative of the activation matrix, covariance matrix. So it's measuring the, not quite the change, but the change of the activation field itself. And what we're trying to do is determine how the error will diffuse across the matrix when the matrix multiply occurs. And we can use that to then steer the algorithm back to where we want it to be. Steer the matrix multiply by using the direction. Essentially, it's the second, so it's not really direction, but we're diffusing. We're determining the diffusion of the error. How does that error spread out when it occurs, so we can then take that and do the opposite and put an error in a deliberate place, a correctional error, but it's still an error in the original data, in the weight data, that pushes that error back and corrects the number. So I'm not sure this really helps, but this picture is basically saying, these outliers, they affect, because you can sort of see the effect of the matrix multiply. A big outlier, for example, it's going to push an error here, spreads out a lot, because it's a big error. So you can kind of this is an approximation of a Hessian, you can kind of see that error here. It's going all along these, and if you notice, it seems really regular. It's diagonal. Yes, it is, because your two-dimensional matrices and blah blah blah. But yeah, so you can kind of see it. So once we have the Hessian, we can then use that to compute each column as we go through the pre-process. We can do it in a fixed order and say, right, adjust this value, and it's then an iterative through system solving this this error diffusion. We use Cholesky factorization, and it's fast. And at this point, you're getting into the kind of what fast means. Well, on 175 billion model, weight model, it's a few GPU hours. It's, however, gets very expensive for much bigger ones. So there are various ways of doing approximate solutions to this, because Hessians are not cheap because they're quadratic. You know, this matrix gets bigger, this thing gets really expensive. So there's a whole science or algorithmic development of faster way of determining this that doesn't, because there's, you know, it's kind of MPs, that stuff. So yeah, there are in practice you can do this directly and just solve it, but for large models, yeah, unless you've got a lot of time or a lot of compute power, you use approximations. And so these two techniques are pretty much the standard, right? If you're quantizing, and to be honest, I don't know, but I wouldn't be surprised, even if you're quantizing to FP8, you pretty much want to be doing this, right? There's no good reason not to, particularly for AWQ. It's so, as long as you've got calibration data, it's pretty much free. It's a one pass of the data as long as you've got enough calibration data. GPTQ can be expensive because of the need to do the Hessian inverse and the Cholesky or whatever other I'm using, but it's still a once-off done. This is purely to the weights. You know, there's no extra data. We're just manipulating the weights themselves before we quantize it. So it's kind of a one shot. It's like a post-training sort of thing. You do your data and then you just go throw it at some computer, and it turns out weights that are more quantizable. And this is just a little summary just to show you, you know, all those techniques. They both require calibration. AWQ is pretty cheap, gives you a good result. GPTQ is much more sensitive. You know, you can overfit calibration data. You have to get the order right. It involves math, so it's more expensive and statistically difficult. But at the same time, it's still not that hard. So you probably want to use both. And it is worth noting we are purely talking about weight quantization here. Though we use activations for the calibration, you know, we use examples of activations we've seen in the real data set. This doesn't do anything to the actual activation quantization. So for example, you would call this W4A16, 4-bit weight, activation 16-bit. So that's pretty much that part of this video. So if there's any questions, next we'll move on to activations, but fire your questions away if you've got any.
I only have maybe one quite dumb question, which is just, you know, throughout this process, actually, in the first part and this part, obviously, a lot of this relies on measuring accuracy and error. Yep. And I just wanted to touch on that. How do you actually measure that? How do you know accuracy and error, you know, what's being affected, and use that to do the optimization process?
And the answer is there are lots of different methods, and none of them are completely 100%. Ultimately, the kind of the real one that you really want to use is that you change it, you push a real through the real model, you calculate the perplexity error or some other metric like that, and that tells you. In practice, that's just not possible. So generally, you're comparing it against the unquantized version of the matrix. So you push through your calibration data through the BF16, say, for example, which tends to be the unquantized one version now. and then you determine the error from the quantized value compared to that and do the mean square error. So you're basically at this stage calculating the difference between if this was unquantized and this was quantized, what are the errors that we've got when we've done the token at the end, the logits at the end, how far of our logits, if we're doing a full model or if we're just doing the matrix multiply, the hidden weights kind of thing. So you have to pick depending on what stage you're quantizing, and how sort of rigorous you want to be. You're picking the output of that stage. As I say, it actually depends on where you are and how rigorous you want to test. If you want to check multiple areas, but generally, you just run the matrix unquantized, run the matrix quantized, and then compute the error between them.
Okay, cool. And actually, sorry, one more quick question. Forgive me if you did mention this earlier. Between these two methods, AWQ and GPTQ, is one of them more common at the moment in the industry, or do people do both? Or
AWQ is so cheap, it's kind of universal. There's not a good reason not to do it as long as you've got collaboration data. The only reason I could think you wouldn't have it, if you wouldn't do it, if you just don't have either good calibration or no calibration data, which almost never happens today, because you know what you're using it for. GPTQ, it is more expensive, so for simple things you might miss it, you might skip it, but I don't think anybody really would today, because it works perhaps better than even AWQ. It gets you a really good gain, particularly on very low quantization. It's a game changer when you get below 4-bit. So today you perhaps don't do it for the higher quantization levels. You can get away with it, particularly things like FP4 and stuff. But it's always worth having. You probably checked it anyway. You probably did it once and saw if it got a gain, and if it didn't, you just didn't use it. I don't think you would really, if you have the calibration data, you would do both and take the cost. And it is worth. I didn't mention it here, but it's worth to bring it out. Yes, they are compatible. So you generally do both. A good quantized data set, especially at low bit rates, will almost certainly have done both.
Cool. And the calibration data, I assume, is just another holdout set. Essentially, it's just more of the training data held out for this purpose. So as long as you planned ahead for that,
yeah, exactly. It's ultimately just an example set, data set, and as you say, this is something that the actual train has had to use so much more. So you can pretty much find a good set. And indeed, because quantization is often done as a later process, often there are, in fact, what most of us use now is there are standard kind of problem-specific data spaces, and you just kind of accumulate a bunch of them to throw it at it. You just go and Hugging Face and get the wiki source and a coding source, and because there's just enough out there that it's fine for this level of usage.
Right, gotcha. Thanks.
Okay, so third part is going to be activations. So far that was all lovely weights, and it was all done to pre-process. We just did it offline, saved it in our tensors, and forgot about it. You can't do that for activations. The data itself is coming in real time. It's the actual values that essentially are going through the model, and they also painful. And there's a few reasons for this. Ultimately, they're the same, right? An activation and a weight are the same thing. They're the two numbers you multiply together. But in practice, they have very different characteristics. The first is that their outliers are really, really important. And they're important for weights. It's important to note, we're not saying that you can truncate your weights, but there is a certain, because of the way that, especially when you're using something like GPTQ, you can diffuse the error. The actual values aren't that important. They're they are relatively, just as all sort of neural networks are, they're quite tolerant to errors. The same can't be said for activations. They require these really, it's a systematic, yeah, it's a good word, error, outliers, and they can be 100 times bigger than all the other weights together. And even small changes, errors, just make it go nuts. They're incredibly sensitive, so and spiky, so you end up having to be much more careful with your activation weights. And that's even worse because they're real time, they're coming in live. You can't spend any time like you could for the weights, where you just sent a GPU cluster off for a couple of hours and it went away and computed the Hessian and did all that. Because these are the actual values going through the matrix multiplies from the actual data that's being queried on. And so this is the thing is just basically indicating this. So one channel and you're done, right? So because of these outliers are so extreme, as soon as you get to lower bits, if you look at this, measuring this one column that was expensive, and all our weight values have gone, right? Because it's so extreme that there's just it can't do it, and it's per token. So a token can be the extreme one out of all your tokens you're throwing through it, because this is activation data. It's coming through. It's affecting the whole matrix, even if it's one of the prior ones in the KV. And you can kind of it's just harsh. It really is. I mean, if you look at this this is what it would be if it was kind of normal, if these outliers weren't so outlier. I mean, it's fairly, the quantization isn't affecting the colors too much. I mean, yes, there's obviously some loss, but things, and then you show what like, because these two channels, which are tokens essentially, just decimate all the other data. So it's like, it's not that they don't just affect what you're doing, they affect all the stuff prior as well. And part of this is because of the actual matrix multiply. Your weights are, on the other axis. Yeah, weights and activations. So when you think of your classic, row versus column, weights are per channel. They're per channel scales, because that's what makes sense. You can't do that because they're per token scales, and a token isn't a very easy thing to do some kind of quick scale determination on. So yeah, it's just, this is the hard one kind of thing, and it's actually in the numerics itself make it harder. So the first idea to fix this, and I say, and it's important to note, we can't do anything too expensive, because we can't just spend a couple of hours on every time a new token goes through the auto regression. Is smooth quant. Now this algorithm is, it's a weird one, but it makes sense in a kind of weird way. If we can't scale the activation per channel, we can scale the weights channels, because ultimately this is a matrix multiply. Both values go into the matrix, get multiplied and added together, so you can actually change the other one to affect the activations in almost the inverse of what we're doing with AWQ, where we look at the activations to decide what to scale our weights. Here what we're doing is a faster version, where we scale our weights to help the activations. What's surprising about this is it ends up being a magic number, and the magic number is 0.5. Now, this is one of the things I just grabbed this for. I've read the paper, my brain reads it. I just don't get why 0.5 seems to be the magic number. I just don't have it's one of these places my brain just doesn't find a logical reason why this is. It's theory, it should be able to range from any of these, and you can kind of see that this migration strength is this magic number, this hyperparameter, and it changes things. And for some reason, when you do the errors, it always comes out at pretty much 0.5. So yeah, I would love to have a really good explanation of why this works, but I don't. But you will see it a lot, that if you're seeing quantization, particularly in activation quantization, you will often see a magic A, and it's usually 0.5. It just works. It's literally one of these things. I'm happy to have anybody explain to me why it works so well. Thankfully, I do understand the next one a bit better, so it doesn't make me look like a complete idiot. And this is the idea of rotating. So we're talking about very big dimensions first. So we both can have the analogy of rotations in 2 and 3D that we're all familiar with, but we also doesn't quite work the same way because we're talking about thousands and thousands of dimensions. So the first thing that does cover across and what defines a rotation is the fact that in a rotation set, the vector length stays the same, right? So any rotation does not change the value of the vector's length. No matter how many dimensions, that's the very definition almost of it. So the idea of why you can rotate your activation data, which in practical terms means you take all your activation values and you just shift them all by a certain amount, to ensuring it's a rotation, a true rotation, and they magically get better. And at first that again is how can just rotating things help? And it actually comes down to a very simple idea. When you do vector lengths, if you think about our original thing that there are big outliers in a particular channel, that means that the dominant part of the vector length is in a single channel. If you could rotate the system so that you spread that length over more of the dimensions of the data point, you're basically reducing the outlier, but keeping the energy the same. And it just so happens to be that there is a particular type of transformation, of rotation called the Hadamard that does this. Now, Hadamard is something well before sort of a classic result. It's not new to thing, but it proved to be the absolute perfect thing for this. And the reason why is it doesn't actually involve you to do a matrix multiply. Traditional rotation, you can format it as a linear transform, so you can matrix multiply. That sounds expensive. But actually, the Hadamard transform only involves doing plus or minus and adds, and then doing some butterflies, moving stuff around. And this makes it extremely cheap to the point of basically 3 when you're talking about sort of the data sizes, the matrix size we're talking about, which is perfect. And so you can just do this pretty simple rotation, the Hadamard transform, give it a rotation, and spread the energy out. And you can consider this. If this is our outlier and it's got a vector length, you've got a magnitude of 10, and here we are, this is horrible. We're going to quantize these. We know that this is going to take up this is going to get quantized to 0. This one's going to stay, but all these are going to get killed because quantization errors. If we just apply the Hadamard transform, we instantly notice that the outlier channel is being spread out. And you just keep applying it, and you end up something like this. And this is much more quantizable. There's a finite range. All the values are spread fairly smoothly over that range. This is just so better like this. And we can quantify it. If you look at the error like this, we'd be at 0.235, and we'd record a vector length of 10.08. At this, the error's down to 0.1, so was that almost, over half? So it's twice as good. The vector length's exactly the same. The energy in these numbers are the same, but none of them have a more of a magnitude than 2.69, whereas back here we had a magnitude of 10. And so this is the basic idea. We rotate our activations so that they are more quantizable, so that their energy is spread out over more dimensions, and that makes them more quantizable. So then the real trick is you can do this for free. And this one is a little bit unobvious. And it's because we are doing both parts. Ultimately, this is a matrix multiply, right? And so you can, if you sort of look at it as a form of linear transformations, you're doing, here are our 8 measures. We do the Hadamard rotation. We then want to get it back out again. So we take the transpose, you rotate in, you rotate out, and then you get your weights out. But of course, Q times QT is identity. So these actually end up being there's no need to do this. You can do this once at the weight stage, and then just multiply K times Q. But that's only a butterfly, because the reason why Hadamard is done is you don't need to do the matrix multiply to apply, and you get the result. And this actually ends up being practically 3. The actual rotation is done to the weights. So you pre-rotate your weights knowing they're going to do n numbers of Hardeman transformations. And then when you apply them, actually in the inference, you just do the kernel fuses the butterflying of the values, moves the data around basically, because the Hardeman transform guarantees that it's just a matter of moving things around, because it only ever does plus or minuses and a butterfly. So the actual there is no extra matrix multiply. It's just move some data around in the kernel and pre-rotate your weights offline, and you don't have to. Yeah, so you know it feels a bit obvious. You essentially do the rotation bit beforehand in the weights and just magic the numbers at the end via some moving of data, which doesn't cost a lot because we just bake it into the kernel itself. Which leaves the only real free sort of parameter is what to rotate by. And this leads to, I think it's one of my favorite sort of little things, Quarot, which basically says it's random. So one of the properties of multi-dimensional, big multi-dimensional sort of hypersystems is it's actually, any rotation actually is pretty similar to any other rotation around a particular dimension, right? There are so many dimensions you can rotate around because of the thing. There's a fairly good chance that all of them or any of them only affect a small amount of data anyway, which you can kind of use to your advantage, because it actually means that purely random is probably pretty close to perfect. It's not. You can do better, and that's spin rot, which then actually does learns the rotations by calibrating it beforehand to pick the rotations that you're going to choose to even your energy out of your calibration data. But amazingly, just randomly picking the rotation values across the dimensions gets you most of the way there, to the point that some people just say, yeah, what the hell. Yeah, and it's just one of those properties of big hyperdimensional systems that yeah, rotations don't work like they do in 2 or 3D, where it makes a big difference. Up those kind of dimensions, they're all roughly the same. And so yeah, and it's still a place where people are investigating this, the research. I mean, Spin-Lock Quat is a good paper, but there are still papers on this stuff trying to work out faster or better rotations and different things. There's been some really interesting papers fairly recently about improving this and using it for things like KV cache, which ultimately are just activations in a way. And so yeah, it's very much some work that's been done on to prove some of these stuff, to actually make the choices better and just generally tune this, because this is the kind of frontier of activation quantization, because we don't really have a good method apart from doing this kind of rotation. Yeah, and so this is the problem and what we do. If you try and do it just per tensor, kind of like you would thought, it's not going to work. You just can't do it, or at least not for low bits. Smoothing quant works just a bit weird. Just kind of, it makes sense. It's done once, but it's not obvious why this works as well as it should. It should just be a relative low thing. And then rotation is where the sort of current edge of the research is going on. But if you can improve your rotation data, you can kind of yeah, there's results there to be gained. So any question on that?
I suppose of those 3, would it be yeah, intuitively it feels like the rotation is the most kind of error-free, or the most of preserving of.
So the weird one is smooth quant just works, right? Again, it doesn't do. It's just you just apply it. You if you're going to be doing it, you kind of, yeah, you can do it and thing. Rotate, yeah. The first one, it just doesn't work, and rotation is where, yes, it's where you get the gains. Some of the data we pulled out, you know, when I'm doing some work on int4 things. Basically, activation at int4 is terrible unless you do some rotations on it. And you can get pretty good recovery of your errors just by, you know, doing some of these rotation algorithms. It really, in some ways, you could say it's the rotation algorithms that make extreme quantization down to int4 of activation data. I don't think you can really, you know, technically you can, but the errors build up so quickly that, you know, practically you've got to be doing it. It's that good of a system. But it isn't perfect. It's still, it recovers some of the error, but it's still activations are where your errors are going to come into. Yeah. So, yeah.
Sure. But I like it. It makes intuitive sense, even just thinking in 2 dimensions of just like a Pythagorean triangle, like the hypotenuse is longer than the other side. So if you can rotate it onto an axis, then the magnitude is lower. It's
yeah.
Cool.
Yeah.
But obviously in many, many, many more dimensions.
Yeah, that's the weird thing is you being trying to use your mental thing, and I'm very much from graphics, so you know, I'm used to thinking 2 or 3 digits. Occasionally, it catches you out when you like the whole quantization, the random numbers. It's like that makes no sense because my brain doesn't want to think about the 10,000 dimensions and how, yeah, actually, but it, you know, it makes sense and it works. But yeah, it is nice to have something that has some mental reference that actually holds across the, you know, the insanity of 1,000 dimensions, because a lot of it is the same. It's
yeah,
that's
cool.
Okay, so actually, I think we've got about a little bit longer. I'm going to do part 4. So this is new. So we covered in part 1 basic quantization. So here we're going to go to actually what the silicon's doing. So we're going to go a bit lower, and that's basically floating point and exactly how this works for on NVIDIA and AMD and Google hardware. So we're just going to go to the next level down and why this is actually quite an important thing, because FP floating point helps a lot for LLMs. So first of all, we have to start with what is a float, and I'm sure this is preaching to the choir, but you know, you have a sine, an exponent, and a mantissa, and if we look at our lovely tick line, we can see basically what happens at each of the exponents. Our ticks get a little bit further apart. So rather than our integer, all our ticks are linear. We now have at each exponent, our ticks get closer. We get the same number of ticks in each area. That's your mantissa, and you know, things. So you can probably instantly see when we looked at our original data about how most of our data is around naught. This is obviously, there's a negative version as well. You know, you can see how this helps with when most of your data is around 0. If you're interested in graphics, right, that's why depth in graphics is registered in floats as well, because things closely are more important than further away. But you can instantly see for LLMs, yeah, most of our data is around 0. Floats instantly look like a bit of win. Further away, you know, the outliers, yes, they're not as accurate, but they can hold the values, which is exactly the properties we asked for. So that naturally led to the concept of quantized floating point numbers. Technically, all floats are quantized, after all, they're not real numbers, but when we're talking about this, we are talking about 16-bit kind of, but really 8 and 4-bit and 6-bit, really small floating point numbers. And so this little just shows that when you get down to exponent 2 and mantissa 2, 1, like things, you know, there aren't many ticks left, but you know, they're still non-linearly assigned. They're non-linearly across the number line. It is worth noting that I think it's shown here. Yeah, it might be in this one. Yeah, this one here, which is this color here, is subnormals. Subnormals are part of the float standards that are weird. Generally, we forget about them, but it does matter when you're getting close to 0. Subnormals are a different encoding. It's not this way, but they have extra precision at very small numbers. And it generally doesn't matter, as you'll sort of see. If you look at the purple lines in here, you can barely see it above thing. But when you're down at exponent nice 2, it actually matters. And so often the hardware still does normalize numbers, subnormal numbers, even on these tiny bits. Just a bit of numerical trivia. So why does this matter, and why are the formats we've got what they are? So if we take our lovely FP32 value that we're all float that we're all so happily used to, we can get up to 3.4 e to 38, lovely big numbers, and you know, that's great all around 1, 0 root around the center point, all great. And we can see lots of data. That's our 32 bits split into the 3 components. So the first FP number, that quantized FP number, is FP16. And it's a bit rubbish. So you only get up to 65,500 maximum. And it has a lot of mantissa range, which doesn't seem to be very useful. And the reason is because it wasn't designed for LLMs. FP16 predates the AI craze recent and comes from graphics. FP16 was designed for storing light values, which were the first kind of things in graphics that could have very large values, but needed to work with things that also were non-linear. So the sun is the classic example. In the average scene, the sun is 1,000 times brighter than your normal lights in your house. When rendering got to that stage, when we need to start to incorporate that, FP16 appeared. But pretty soon, as the hardware started to shift to AI, realized that this really wasn't the best way. And so we got BF16, Brain Float 16, I think Intel christened it. And in this case, they started to look at how the numbers are used, and they realized that if you're going to have 16 bits, it's much better to have more exponent than mantissa for this thing. So they took a 32-bit float and they chopped the bottom 16 bits off. So, so you can have exactly the same range as your floating point 32. You can have all the numbers up to this huge value, but the actual ticks inside that are much smaller. And that's much more useful for weights and activations and general data and things. So at the moment, these 2 words are often used interchangeable, but at the code level, always check, because you want this one. Pretty much for all the data you're doing, LLMs and stuff, you want BF16, not FP16. They take the same space up, they just have 2 different uses. And this is interesting because this exact problem, or this exact decision, but with better naming, came about when you get to FP8. Again, you have a choice. How many exponent bits versus mantissa bits? And when you start getting to really small things like FP8 and lower, this starts to actually matter whether or not you're training or inferring. The actual date, what you're doing on the calculation, which bits you're putting using the most, choosing to use, start to matter. And so FP8, there's actually 2 types, EE4M3, where we basically keep a reasonable amount of mantissa, a reasonable number of ticks, and also E5M2, where we want the range, but we're less care about the actual divisions. So this is so you already start to see as you get down to these lower bits, things that you generally don't have to think about, like with floats, about what's a mantissa, what's an exponent, start to matter. And and the general way has been to just support all of it. The hardware just thinks, but you have to be careful. Some hardware doesn't, some does. Pick the wrong one and your calculations can all go to rubbish. So yeah, it's worth noting that they are different. And then you get to the extreme. Arguably, you can actually get an FP3, I've seen, but nobody's ever supported it really. FP4, so you're going to 4 bits. One of them's just sign, because unfortunately, LLMs and weights require sign data. Actually, in graphics, some of our small values did lose the sign bit, so you only have positive floating point numbers, but for weights that doesn't work. So you have 2 bits for your exponent and 1 for your mantissa. And the extreme of that means there are only 16 values total, and they go between -6 and +6. It's like you can enumerate all of them. It's kind of funny. You often find you build tables to fast convert this, and you just write the table out in whole. But as you can see, the key point is it's non-linear. Around 0, you can store -0.5 and 0.5, but between 4 and 6, you can't store 5, right? There's no value in between them. So there's, you're trading a reasonable amount. I don't know if 4 values is reasonable, but between at the roundabout 0 for a very low cap 6 or -6, and virtually no precision between that. You can't even get down to integer level between 4 and 6. But that trade becomes a benefit because you've got a non-linear 4-bit format. And the way you get around that, of course, you go back to our first thing. It's all about your scale and quantization and how you do scaling. As we said, everybody does blocks because that's the only one that makes sense. And so that would be a thing. What is interesting is here what the hardware innovated on, realized that having a floating point 32 float value scale wastes a lot of space, and so they don't. And what they do is they use quantized scales as well. So now you've got, for example, for MX, which is the open standard, it's supported by a bunch of different hardware, Google, AMD, NVIDIA, and it's sort of an open standard. And so what it has, block size is 32. So it has 32 4-bit values and then one 8-bit value for the scale. And this one's a real weird one. It's EAM0. Now, EAM0 means that it's just a power of 2. It's effectively, it can only represent the power of 2s. It has, and nothing else. And so every 32 values of the MX formats, you get a power of 2 scalar effectively. And if you're kind of an integer shifty boy, it feels very much like us shifting integer values around, because it's basically the same thing. It's just a floating point equivalent of a shift. And they support 4 and 6 and 8-bit for this. And this is the kind of generalized format. Now NVIDIA, for the Blackwell hardware, came along and obviously did a lot of data thing and saw that they could do better. It's possible that the other hardware at some point will get better ones, but NVIDIA is ahead, and I guess they had to compromise on the MX formats because it's a cross-bender thing, and you know, however it works. Maybe some do it by bit shifts and stuff. So NVIDIA chose as their chosen format, 4-bit format. It's every 16 values, they have a FP8 value, and specifically it's E4M3. And then they have an additional floating point 32 scale for the whole tensor. So what they do, what they're cleverly doing is this single tensor scale is scaling the low precision scalar value. So you're it's actually a tiny amount of extra hardware, but by doing this, they can use a very small scale on each block, but still have the overall range that they need to catch all the values. And this works really well. I mean, you can this is comparing the two here at various the blocks max, absolute max, and you can kind of see, I mean, even without really knowing what these colors are, you can see this one is a lot worse than this one, right? I mean, you can go and look at the actual numbers and the misfits and data, but it's ridiculous. And the reason is, if we can just get it on here, essentially what the problem with the MX formats is 8-bit, pure 8-bit exponent, is that it misfits up to the next parity scale, and then it's close again. So it's a very much gets a lot of error, okay, not too bad things. Whereas NVIDIA's actually keeps the error constantly fairly low. Sure, you know, there's a little bit of error in that top there, but it's never huge. There are certain values that just MX FP4, for example, just wrecks. I mean, look at that. That's an error and a half there. I mean, that's our data range. So you can kind of see, yeah, NVIDIA FP4 is good. NVIDIA advert over. So what does this mean? Well, if you actually look at this from our actual error between the sort of different systems, if we have int4 here, so this is a block 16. So every 16 values, we have a 32-bit scale, which gives us a bit for width of about 6 bits, because 64 of our block here, you know, they're 4 bits each, whereas 2 per byte. So it's 32 bytes for all of them for the actual quantized values. And then their extra scale adds on. And because every 16 values that are in for one here has a full 32 bits, it actually ends up being half the quantization on the scale. So this 64 weights, you're going to save, you know, down to 32 bytes for your quantized value, and you then add 16 bytes of scale. So you end up with 6 bits per value overall. For our for MX FP4, you do actually better here, because you're only doing a FP8 scale every 32 values. So your actual overall bit width is actually really low. It's like 4.1, because you've got most of the data's you know, 4-bit like here, and you've just got 2 8-bit values out of the 64 block, which is your 2 scales. So from the size wise, this is really good. But if we look at our errors, clearly it's not even getting up to what our int4 did, a 6-bit int4 did. And then NVFP4 sits right in the middle. So its bit is 4.5. It comes out as, do the math if you want as well, 16 blocks, 8 bits, So you get 4.5 bits effective per weight, and your error metric is pretty much between the two. So you get close to a 6-bit quantized, 6-bit space quantized value for the cost of 4.5. And you can kind of do things, and it shows it how across the different values and those things. And in fact, in some cases, NVFP4 can actually beat the int4 and higher with a full scale because it's more concentrated. So just generally, if you've got a choice, this is what you're fighting with. If you've got Blackwell, you pretty much start on NVFP4. It's good. And if you haven't, you're then having to decide what's the values. And this goes back to the last thing about rotations or GPTQ. These can really help int4 and MXFP4 recover these problems. NVFP4 largely doesn't need them. It doesn't get much better because it's already preserving the outliers pretty well. Its actual data format is capturing the data better. So these two, you often find you can really get your error rate much better by applying these kind of techniques to condition the weights better and the activations better. NVFP is much more just, it doesn't care. It doesn't need a much more condition of the data because it's a better capture of the actual the properties that the LLM wants to keep. So this is a little bit probably too low, but anyway, it's worth it quickly. So the Blackwell hardware I mentioned in the other video has explicit hardware to do this. So it not only gets the benefit from memory and bandwidth, it physically gets acceleration. However, there is some little wrinkles, and one of them is, and I'll show this in probably in the next video I do. This format W4A16, which is quite a good one in terms of getting good error rates, really Blackwell doesn't like, and the reason is that their hardware only does quantized FP values versus quantized FP values. It doesn't do FP4 times BF16. So if your activation is 16-bit and your weights are 4-bit, it physically has to dequant and then run the MMA, which slows it down considerably. Whereas if you can get both your weights in activation of 4-bit, you go through the actual fully hardware stage. And I've measured this. This actually works really well. I mean, you get a good, decent speed up when I've measured it just from this simple optimization. And so it's just interesting work. There's a whole bunch of other things you need to do at this stage as well, like CUDA, RAS, and Fusion for this to work. But it's actually worth noting that when you're at this level, it's not just one of the formats. You have to start considering both sides of the matrix multiply to hit the fast path on the hardware. And this is just to complete up. This is actually what's in the hardware today. NVIDIA Blackwell has pretty much everything. And both AMD, the latest consumer, has FP8 quantization. They don't have sub in the consumer and RDNA 4 yet. So the best quantized format they have is FP8. Their data center, the CDNA stuff, does have a little bit more support, but it's still nothing like NVFP4. And I expect the vendors will be correcting this pretty soon with their own little custom versions if they're not allowed to use NVFP4. But yeah. Okay, any questions on that?
Just a weird thought, right? So all of these data types seem to assume symmetricity between the positive and negative values. So are there any data types that don't assume that the positive and negative values are symmetric?
In hardware, no, and I don't think any of the inference engines support it. The original sort of research and paper absolutely had asymmetry, and indeed, I think when I first wrote this, I actually mistakenly said scale and bias for the block format. In practice, it's been found that it's just not worth the extra value So it's kind of gone away, and certainly at the hardware level, they've completely rejected it. It's just not worth the extra cost of another value, but it does get slightly better. So if somewhere along the line it proves to me some reason it makes it, you know, becomes worth the cost, they will bring it back in. But for LM values, because they're so sort of around zero, I think it just makes sense to let it go and save the space to store the bias.